Hello, my amazing students. We are on page 31, and so make sure that you're filling your notes out as we follow along. We are covering topics 4.7 and 4.8. There are three types of chemical reactions that we need to be aware of, and one is an acid-base reaction, and so that's why I put these together. So there are three types of chemical reactions that you need to know what to do with. We have acid-base chemical reactions, acid-base chemical reactions like neutralization reactions. There's also oxidation reduction reactions, and then the last one that we have been working on quite a bit is precipitate reactions. So those are the three types of reactions that we're going to talk about today. So first off, what is an acid and what is a base? We have two definitions of acids and bases. We have a Bronsted-Lowry definition, and then we have an Arrhenius definition. The Arrhenius definition is really great for making quick assessments, but it's not perfect. It doesn't encompass everything that our Bronsted-Lowry does. So here's the Arrhenius definition. In general, okay, and again, we're talking generally. Acids, their chemical formulas start with H. So like hydrochloric acid, HCl. Okay? Another example of this would be a sulfuric acid, which is H2SO4. Okay? So these are like in general, and not always, and we're going to see it down here, the chemical formulas for acids start with a hydrogen. Bases, on the other hand, tend to end with hydroxide. So sodium hydroxide, OH, that's a really common strong base. Another one that we could talk about would be like a calcium hydroxide, so CaOH2. So if we're ending with OH hydroxide, then it tends to be a base. Okay? Acid solutions have a whole bunch of H plus aqueous ions floating around. So there's more H plus than there is OH minus, and that's what makes it an acidic solution. And then our bases, solutions, they have hydroxide ions in their solution that makes them a base. Okay? All right, so that's our acid base as far as the Arrhenius definition goes. For our Bronsted-Lowry, though, we need to know that acids are H plus proton donors and bases are proton acceptors. And so let me show you what I mean. So first off, hydrogen. When hydrogen is neutral, it's got one proton and it's got one electron. And then there's a couple different isotopes of hydrogen, and so we can have different numbers of neutrons. So now we're just going to say 0 neutrons for now, okay? But there could be different number of neutrons. If we make this an H plus, that means we've lost a negative electron, and so we've lost this electron. So acids are hydrogen donors or proton donors, and see how this H plus is essentially only a proton? And so that's what I mean there. So H plus, and then bases are hydrogen receivers, like they receive a hydrogen. So acids donate a hydrogen, bases receive a hydrogen. Okay, I'm going to rewrite this formula. So we have HCl plus H2O turns into Cl minus and H3O plus. Okay. So look at what happens here. The HCl is going to lose a hydrogen. Like, do you see how it turns into Cl minus? So it's going to lose or donate a hydrogen. That makes this the acid. Water, on the other hand, the H2O, turns into H3O+. So it gains a hydrogen. So that means when something's going to gain a hydrogen, that it's the base. That's for the forward reaction, right? Like these things turn into those things. But it turns out most of these, and almost all of them, to some degree, they're reversible. That we can go this direction, we can also go back the other way. So if we think about that for a minute, this Cl-, if we're looking at a reverse reaction, it went from Cl- to HCl. So this is going to gain a hydrogen, and that's the definition of a base. And then H3O+ is going to become H2O. So this is going to lose a hydrogen, and that's our definition of an acid. Now, to distinguish between reactants and products, we just add the word conjugate. And so this is a conjugate base, and this is our conjugate acid. Let me get spelling really quick. Oh, it's a J, sorry. It's going to be a J. Okay, so I'm going to spell it out. So CONJUGATE, conjugate. Conjugate acid, conjugate base, and it's just on the product side. But what's cool is it's always connected to the opposite. So if this is the acid, then what it turns into is a conjugate base. And if this is the base, then what it turns into is a conjugate acid. Okay, we're going to do one more of these together. So H2SO4, and look at what this is going to turn into. HSO4. So this is going to lose a hydrogen. So if it's going to lose a hydrogen, that means it's the acid. And the thing that it turns into is a base. So it's our conjugate base. Where water, and it doesn't always have to be water, we'll see that on the next one, but we had 2 examples with water. And this turns into H3O+. The other name for this is hydronium, by the way. H3O+ is hydronium. So we have water, and it's going to gain a hydrogen, so that's the base. Bases gain. They're a proton receiver or a hydrogen acceptor. And that's going to mean that this is the acid, but it's a conjugate acid. Okay. Nice. All right, so that's identifying if it's an acid-base reaction, like are we gaining and losing hydrogens, okay? Okay, let's keep going on to oxidation-reduction reaction. So we're on page 33, 33. All right, so during oxidation-reduction reactions, items that are reacting are gaining and losing electrons. That's what makes it an oxidation reduction reaction. So on our last one, it was gaining and losing hydrogens. That's what made it an acid and a base reaction, where for oxidation reduction, it's actually the gaining and losing of electrons. And we're going to use something called oxidation numbers to determine, first off, if it is an oxidation number, and then to decide which ones are gaining electrons and which ones are losing electrons. So we're going to go over the rules for oxidation numbers, and then we're going to use that concept later. So just know oxidation numbers are what's going to facilitate us to be able to determine if a reaction is oxidation reduction reaction and what is oxidizing and what's reducing. So rule number 1, if anything is in its pure elemental form, it's not an ion, then the oxidation number is always 0. So if you just have magnesium all by itself, its oxidation number is 0. Iron all by itself, its oxidation number is 0. It could be diatomic or even like triatomic molecules, but it's just one type of element. It's only hydrogen, or it's only oxygen, only chlorine. Okay, all of those would have oxidation number of 0. Now, for monatomic ions, so not polyatomic ions, monatomic ions, it's the metals and the non-metals. Whatever their charge is for the ion, then it's also, the charge is also the oxidation number. Okay? So let me give you an example. What if I took zinc chloride and I'm going to have it react with copper, solid copper, and this is going to turn into copper chloride, and then, and actually, what should I do for a charge on copper? Because there's a couple different options. Copper ion charge. Yeah, 2's a possibility. Let's run with it then. And so then copper chloride, and then the zinc is going to be the solid now, okay? So if I was doing oxidation numbers for this, the copper is not an ion and the zinc is not an ion. It's elemental. They're all by themselves, and so this has an oxidation number of 0, and that one has an oxidation number of 0. This is an ion, though, because it's a metal and a non-metal. So whatever the charges are of those ions, that's the charge. That's the formal, sorry, I keep saying, that's the oxidation number. So because zinc has a +2 charge as an ion and chlorine has a -1, those are the oxidation numbers. So we get +2 and -1. Okay. Now copper, because it crisscrosses here for a 2 and a 1, we know that it's a +2 and this is a -1. So those are the oxidation numbers. Okay. Next, rule number 3. Molecular compounds. So if oxygen is in a molecule, then we assign oxygen the oxidation number of -2. So let's talk about H2O really quick. And I'm actually going to jump down to the last rule because it's going to help us with this. The sum of the oxidation numbers equals the total charge of the molecule or the polyatomic ion. So like for water, it isn't plus or minus anything. So whatever my oxidation numbers are, it needs to add up to equal that charge, but for all of the atoms. So here's what I mean. We know that oxygen, this single oxygen, is going to have a -2 oxidation number, because that's my rule. That when oxygen is part of a molecule, it gets a -2. But this whole molecule is neutral, it's a 0. So that must mean that each of those hydrogens have a +1 for their oxidation number. Because 2 of those with +1 and then the -2 would all together give us a 0, right? So the oxidation number for the hydrogen here is going to be a +1. And the oxidation number for the oxygen is -2. Okay. Let's do this again for carbon dioxide. CO2. Okay. Each of those oxygens, both of those oxygens have an oxidation number of -2. And so for this whole thing to be 0, then the carbon must have an oxidation number of +4. So oxidation numbers would be +4 and -2. All right. When hydrogen, rule number 4, when hydrogen is bonded to a nonmetal, just like oxygen, then it has an oxidation number of +1. And look at that. That worked out perfectly. Oxygen is a nonmetal, and each of the hydrogens were a +1. When hydrogen is bonded to a metal, though, then it has an oxidation number of -1. And this worked out well as well. Because look at this one. This whole thing together is going to be neutral. It's going to be 0. The hydrogens are each -1 because they are hydrogen and they're with a metal, and magnesium is a group 2 metal. Like it has an ion where it's a +2. So the single magnesium is a +2, and then we combine it with 2 -1s so that the whole thing is neutral. So the formal charges would be +2. Oh my goodness, not formal charges. Oxidation numbers would be +2 and then -1. Okay. Rule number 5, and we've already done number 6. When there's not oxygen or hydrogen inside a molecule, then what you do is for the atom that is the most electronegative, whatever its ion charge would be, then that would be the formal charge. Okay, so like EF3. Okay, so fluorine is more electronegative than boron. And when fluorine is an ion, it's not an ion here, but when it is an ion, it's in group 17 and it has a -1 charge. Okay, and so that would mean that the oxidation number for each of those fluorines is -1. In order for the whole thing to be neutral, then boron must have a oxidation number of +3. So then our oxidation numbers would be +3 and -1. Okay. Now, phosphorus and chlorine. So neither one is oxygen or hydrogen, so I can't just automatically assign plus or -1 or a -2 for the oxygen. So I go chlorine is more electronegative than phosphorus is. When chlorine's an ion, it's in group 17 with a -1 charge, so that must be the oxidation number for the chlorine, but there's 5 of those. So the phosphorus has to be a +5. So phosphorus, its oxidation number is +5, and chlorine is -1. Okay. So we just did this one, actually. In class, we're going to do those ones together. So let's look at the bottom of page 34. How can you determine what gets oxidized and what is reduced? The word after that is supposed to be reduced. Reduced. Okay. What we're saying is, how do we know when something is gaining electrons or losing electrons? And there's this really silly way of remembering this. Okay. Leo. Okay. Leo the lion says grr. Okay, Leo the lion says grr, and here's what it stands for. Losing electrons is oxidizing. Losing electrons is oxidizing. Gaining electrons is reducing. Another thing that might be helpful is when something reduces, when it gains electrons and it reduces, the oxidation number reduces. Okay, and so if the oxidation number gets bigger, it's oxidizing. If the oxidation number gets smaller or more negative, then it's reducing. So let me give you an example. Calcium is elemental. It's all by itself, so it has an oxidation number of 0. O2 is elemental. It's only oxygen. It's not an ion, only oxygen, so it also has an oxidation number of 0. Now we have a combination of calcium and oxygen. So as soon as oxygen is combined with something, we give it a formal charge of -2. And since we need both of these together to be neutral, calcium must be a +2. Okay, so calcium went from being 0 to a +2. Okay, its oxidation number went from 0 to +2. Where oxygen, it went from 0 to -2. So if we have a 0 to a +2, that means that we lost negative electrons, right? So 0 to +2 means that we lost negative electrons, and losing electrons is oxidizing. So this is oxidizing. So calcium oxidizes, it's going to lose electrons. Oxygen is going to reduce, it's going to gain electrons, because if we go from 0 to a -2, we gain 2 negative electrons. So this is reduced. Okay. If your oxidation numbers change, then it is an oxidation reduction reaction. if your oxidation numbers do not change, they stay the same, then it is not an oxidation reduction reaction. Okay, we're going to do one more of these together. So I'm going to decide what's oxidizing and what's reducing, okay? And I need to do my oxidation numbers first to figure that out. So here we have oxygen, and it's combined with chlorine, and it's combined with potassium. So I'm going to assign a -2 to each of those oxygens. Okay? So then after that, I can think of these other ones as their ions. The whole thing, though, has to equal 0. Okay? And so chlorine, and this is a chlorate, this is a polyatomic ion. So ClO3, okay? And this whole thing has a -1 charge. Okay, let's focus on that first. So you don't have to have this polyatomic ion memorized. Let me just help you with this. So if each of the oxygens are a -2, then this chlorine must be a +5, because -6 + 5 would give us a -1. Okay? So this is going to be a +5. And then it's combined with potassium, which is a +1. And so all of these together would make it neutral up here. So I also know that these are ions because it's a metal with this polyatomic non-metal. And so that would be an oxidation number of +1, +5, and -2. Okay. Now let's look here. Oh, I see another polyatomic ion actually. This is NO2, so it's not nitrate, it's nitrite. And this whole thing, NO2, has a -1 charge. So each of the oxygens are a -2. The nitrogen will be, what is that, a +3? But here's another cool way of figuring this out. So we have, and actually that polyatomic ion, so 2 nitrogens, a +3, and then this hydrogen is a +1. Okay. Now, like I said, here's the other cool way of figuring this out. Remember when hydrogens are with nonmetals that they're positive? So we could assign the -2 to the oxygen, the +1 to the hydrogens, and then we know the whole thing needs to be neutral, so this nitrogen had to be a +3. Okay. We have ions again. We have a metal and a non-metal. So chlorine's in group 17, so it's a -1, and potassium's in group 1, so it's a +1. And then we have something similar here. We have hydrogen with nonmetals, so it's going to be a +1. Oxygens are each -2. And so then the nitrogen has to be, let's see, and this whole thing's going to be -1, so was that +5? Yeah. I see a nitrate, NO3, and the whole thing's a -1. And then the +5 + 1, so that's a +6, and it cancels with the -6. So +1, +5, -2. Great. All right. What's oxidizing and what's reducing? So potassium went from +1 to +1, so it didn't oxidize or reduce. The chlorine went from +5 to -1. Okay, so we definitely reduced our oxidation number on that one, and we did it through gaining electrons. We gained 6 electrons at the lot to go from +5 to -1. So this is reducing. Oxygen was -2, and then it stayed -2, so the oxygen didn't gain or didn't oxidize or reduce. The hydrogen was a +1, and it stayed a +1. The nitrogen, though, went from +3 to +5, so its oxidation number increased from +3 to +5, so that oxidized. Okay. It lost negative electrons to become more positive. So here's how I would write the half reaction. So for the reduction half reaction, it's the chlorine that reduced, but I'm going to write the whole thing. So I'm going to say KCO3 turned into, and then I'm going to say what it reduced into, KCl. So that is my reduction half reaction. My oxidation half reaction would be HNO2, and it turns into HNO3. So that's my oxidation half reaction. Okay, awesome. And then we'll do some more examples of that in class. Okay. Okay. On to our last one that we've been doing. So turn to page 38. All right. So this is precipitate reactions. And precipitate reactions, and we've talked about this, precipitate reactions happen when I take two ionic aqueous solutions. So when it's a metal and a nonmetal, or polyatomic ion, two aqueous ionic solutions. They're going to trade partners. It's also called a double replacement reaction. They're going to trade partners, and one of them is going to precipitate. One's going to become a solid. And the one that's going to become a solid will not have potassium, sodium, potassium, ammonium, sodium, potassium, ammonium, or nitrate. Like, those are the ones that are definitely soluble. And I would say a lot of these group 1 metals, and like we have sodium and potassium, but there's also like lithium, rubidium, that kind of stuff. Okay, so let's look at this. I have a sodium hydroxide, so 2NaOH aqueous. And just checking in on this, sodium is a +1, hydroxide's a -1. And that's why they crisscrossed and we didn't get any new subscripts. Plus copper chloride. Well, chlorine is a -1 because it's in group 17. And so then we don't know what the charge is for copper because it's a transition metal, but based on this crisscross, this had to have been a +2. So the 2 went there and the 1 went there. Okay. They are going to switch partners. So the positive sodium is not going to be with the negative hydroxide. It's going to be with the negative chlorine. And the positive copper, Cu, is not going to be with the negative chlorine. It's going to be with the negative hydroxide. But after we switch partners, we need to get the new subscripts. So this is a +1, and this is a -1. Oh, so 1 to 1. So I don't do anything on that one. No new subscripts there. Copper is a 2+, and hydroxide's a -1. Oh, so the 2 needs to go down there, and then we have the 1. Okay. One of these is a precipitate, and one is aqueous. And so if it has any of these things in there, then it's soluble. So it's not the precipitate, it's aqueous. And the other thing must be the solid. Usually what we do after this is that we write the complete ionic, and then we write the net ionic. Okay, so for this one, and this one, I would break them apart into their ions. What I'll find is that the sodium and the chlorine are the spectator ions. There's supposed to be a 2 here to get this all balanced. So those will be our spectator ions. And what we'll be left with for our net ionic will be copper aqueous 2+, and 2 hydroxide minus aqueous turns into CuOH2 solid. Oh, last thing. Everyone, I know that third period I mentioned this. I don't think I mentioned it during second period, so if you're in that class, I apologize. Often, when they want the net ionic, so like when they're trying to get you to solve to tell me what the net ionic is, the phrasing that they will use is reacting species. They'll say, what are the reacting species in this equation? And when they say reacting species, they want to know what the net ionic equation is. They don't want to know what the spectator ions are that cancel. They want to know what is actually reacting, and that would be the net ionic. Okay, awesome. We will practice that as well next class. Thank you so much.